Hello, everyone. Welcome to MABA's fourth webinar of 2023, entitled Responsible Recycling of Phosphorus Extracted from Wastewater, the Limits and Opportunities. My name is Bill Toffey. I am today's moderator. I'm also on the board of MABA, and I'm also on the programming committee. And we've put together this webinar today. It's not about PFAS. Okay, but we wanted to remind you that MABA has enormous resources on the MABA website for those of you who are, for whom PFAS is a major issue. We also have opportunities for you to engage in some of the science that is underway in our region. And please contact us if you are interested or have a client who's interested. No, today's webinar is about phosphorus. And with a slightly different angle than you may have had in the past. We're not particularly interested in just the technology that can save you from struvite buildup or that can help you comply with effluent standards, but rather with how we're looking at the 2 pounds of phosphorus that comes into the wastewater plant from each of our customers each year, and how we can transform that into a recyclable fertilizer, and what those attributes are of that fertilizer. I want you to all adopt my moniker, which is recycled phosphorus first, and advocate for that in your communities and with your farming communities. We have 4 presentations today, and each presentation is approximately 20 minutes in length, with questions and answers going to be handled at the end of all 4 presentations, and I will be watching the Q&A at the bottom of your screen here for those questions you might have, so that we can manage those at the end of the presentation. Now, I would like to kick things off by introducing our first speaker, which I think is, I am really excited because he is new to our webinar series, at least, and he is, I think, new to our biosolids community in some respects. That's Rob Minan. He is an assistant research professor at Penn State's Department of Plant Science. He acts as the director of the Pennsylvania Nutrient Management Education Program, which we could all benefit from. He has a PhD in soil science and an MS in animal science. He's a state extension specialist in nutrient and manure management, focusing on water and air quality issues. He also puts out himself as one of the leading experts on the phosphorus index. He has coordinated education programming for the Pennsylvania Commercial Manure Haulers and Broker Certification Program since 2004. And before coming here, he managed a large sow farm, recognized nationally for both its efficiency and environmental stewardship. And Rob will be presenting on the manure shed management concept for biosolids-borne phosphorus. Rob, I am so excited. Take it away.
Will do. You should see my screen, so I think we'll go ahead and proceed.
Yes, we do.
So thank you for the introduction. It's great to be here. I work in a different world, but a very related world with manure management. So I'm also considered a state extension specialist with manure and nutrient management on Basin University Park, Pennsylvania. I will be conducting phosphorus index training this Thursday with our nutrient management planners in their world. So let's just go through some basics on phosphorus. I think that since I'm lead off, I want to do some introductions on phosphorus because many people can always use a good review. Whenever we look at manure in the state, all manure that's generated or utilized in the state, those farms have to have either a nutrient management plan or a manure management plan. We're not going to go into what differentiates who needs what plan at this point, but I can always talk to anybody about that. Some importers of manure also need a balance sheet, which also gives them a application rate. These plans can be based on nitrogen or phosphorus, depending on some different criteria that we're not going to dive too deep in today. But the plans account for organic nutrients such as manure, biosolids, and food processing residuals. Also count for commercial fertilizer inputs and manure and legume history for nitrogen. Soil testing is recommended with all of our programs, not always required for the farm to put manure in their field. But soil testing increases accuracy, and I always like to pitch these three things: the agronomic, economic, and environmental benefits of a lot of the things we do, and planning and soil testing fit into that. Soil tests for the farms required to have it need to be done every 3 years. And if a soil test has 200 parts per million phosphorus at the farm, it can trigger additional planning steps. So if we look at the amount of soil phosphorus lost, and then the soil test phosphorus in parts per million, we have a lot of data that will show us that in our state, if we get to 200 parts per million, we have an increased risk of loss. So at this point, we do know that we see this loss start to trend up and become a problem in potential pollution for waterways. The good news is that farms can operate down here at the 30 to 50 parts per million soil test level and still get all the phosphorus they need for their crops. So what we want to see is we want to see people at this optimum level of soil test and have them avoid getting too high. But as we apply manures, we know that we can creep up. And this is why. Here's a fundamental challenge of managing manure and crops. The crop need for nutrients in nitrogen and phosphorus do not match with what we provide in manure. So, and if we look at this first half of the chart here, the nitrogen rate, and this black box would represent the corn, but this would be true for any of our agronomic crops in theory, right? The exact numbers are going to be a little different. In fact, I don't even have numbers on here to tell you what we're looking at as far as pounds or per acre. And then fittingly, the brown stripes are the dairy manure nutrient content. So if we perfectly match the nitrogen availability in the dairy manure to the crop need, we will always over apply phosphorus. And that is due to this imbalance. So anything we can do to make nitrogen more efficient will help us reduce that phosphorus over application. But this is traditionally what's happened in many fields for decades and centuries. So what happens if we get to the point where, I'll back up, if we get to this 200 parts per million soil test level, is that's one of the triggers that would force us to manage our farm fields on a phosphorus level. If we manage on a phosphorus level and we perfectly match this phosphorus level to our crop need, so what's in the manure to the crop need, we will always under apply nitrogen. So we have this mismatch, and it does create issues and challenges as we move through our planning processes. Here's the phosphorus cycle as we look at it for manure management. If you look at the red box right here, this is what we want, right? We would love to have all our phosphorus go onto the field through the cycle and exit the field in the form of a harvested crop. That would be the ideal world, but we do get this issue where we have runoff and we have leaching in these red boxes, which can provide environmental threats and are laws that are not economic, not agronomic, and bad environmentally. I like to split this phosphorus cycle. I like this graphic because it has an inorganic side, and these would be things such as minerals and other items that are already in the soil. We have a little bit of atmospheric deposition, and then we have mineral or commercial fertilizers that we can add on the organic side. With manure and biosolids, we're looking at the organic side, right? We have the animal manures and biosolids, plant residues that we can add to the soil surface or incorporate into the soil. And to get those into the plant, we have to move those through the soil solution, right? So this soil solution, this central part of this is very critical, right? This is the hub of the phosphorus index, and for anything to go into the plant, it has to be in a soluble form. In order for this organic material and manures and biosolids to get to this central hub of soluble form, we need microbial processes, some chemistry to occur, but everything centers around that. In agriculture, with our manures, we say that the microbes convert the organic P to mineral P to make it plant available, and that this is at any one point in this central hub, this is at any one point less than 1% of the total phosphorus that is in the soil. So when we test soil, we're actually testing for a lot of parts of phosphorus and trying to figure out how much of that phosphorus can move into this soluble portion and toward the crop in a given season. So that's a good introduction on phosphorus. I've been involved in this manure management world for over 2 decades. And if you go back to times I've managed animals, quarter century, more than that, I've been involved in for a couple years now in this group with USDA long-term agro-ecosystem research systems called manure sheds. And what is a manure shed? A manure shed is a relatively new concept. It looks at areas with surplus nutrients, and we're just looking at animal nutrients, and we call those a source. And then we look at the animals that could receive those nutrients, and we call that a sink. So it's basically, if you're familiar with nutrient management plan, it's looking at nutrient management planning, but on different scales, right? Scales for manure sheds can be farm level, they can be among counties, they can be within counties, they can be regional. I have this map on the bottom. This map is just tons of phosphorus for the swine industry as produced per county in the United States in the lower 48. You can see that we have a concentration of swine in North Carolina. We have a good concentration in Iowa and Minnesota. We have in Pennsylvania our own concentration. And this manure shed concept that we are involved with, we looked at this in a paper. We published this paper last year. I was the lead author on this paper. This is one of perhaps going on 20 papers in the manure shed world at this point that are interested in looking at different concepts. We were focusing with this paper primarily on implementing manure sheds in the swine industry. Here is, but in that paper, we also did a comparison to poultry with swine. So here we have poultry phosphorus by county, and here we have swine phosphorus by county across the United States. You can see that each one of these species has their own hubs of production of nutrients. And this might be akin in the biosolids world to a city, right? You have hubs where you're producing more than others. In particular, in the swine, we compared this Iowa, Pennsylvania, and North Carolina, the smaller hub in our state. And we looked at land mass needs to export the manure away from source areas to sink areas. We also considered where swine and poultry overlap. So if you look at green counties in these maps, up on top, or this phosphorus, down on the bottom is nitrogen. Let's look at the top one. Green counties are pigs, right? Red counties are dominated by poultry. And then when in the middle, we have the orange and yellow counties where we have overlap. If you look in our region here in the mid-Atlantic region, we have a lot of counties that overlap. We have multiple species. So for us to look at a manure shed concept for one species is not quite fair. Here we're just looking at poultry and swine. A colleague of mine, Dr. Robert Mikesell, who's I've been the principal investigator on this grant, but he works on the grant through Department of Agriculture for 20 years, has done an odor evaluation service. This is looking at potential odor conflict for proposed new farms. This does not mean the farm has been built, but primarily Country View family farms in the swine industry and Bell and Evans poultry have looked at this for over 20 years. And every time they want to contract and build a new site, a new manure source, they go through this odor evaluation. So they're concerned about the possibility of offending neighbors. But let's look at this. Here we have 5-year periods from 2000 to 2005, down another period from 2016 to 2020. And in between, on this first column, we have hogs in the graphic. On the second column, we have birds. And we look at where we were. Poultry and swine have developed different avenues of where they look to build farms. If you look at swine, they were primarily in the south central area. And over time, you can see that they have shifted north and west. Poultry, they were in a central PA area, and over time, they still have remained there. So they have not moved so far. But hogs have been shifting where they build new sites, where they create new sources of phosphorus. What's the primary difference? Swine is handled as a liquid, poultry handled as a solid. So we have different handling systems, different manure constituents, different properties in our manures, different phosphorus partitioning. Another important factor, if you look at the swine industry, country veiling farms are shifting their animals all the way down to the southeastern portion of the state, whereas Bell and Evans are located in Lebanon County and they're central. Well, pigs can move a lot further and transport to the harvest facility. Birds, not so much. They want the birds to be closer. And this gets down to an animal welfare system. So if we think about nutrient movement, phosphorus movement, where would we like to see phosphorus? We would love to see all the phosphorus move to areas where crops can utilize it. But here you have an industry in the poultry industry that doesn't move because they want to keep their ride for the birds when they leave the farm to go to the harvest facility 90 minutes or less because of product, consumer product demands, the tastiness, the properties that go into a good piece of poultry, a good piece of chicken, and welfare issues as well. Swine industry doesn't have to worry about that so much. So what are some of the expansion drivers? We mentioned the odor sighting index. We mentioned this distance. Swine, what the expansion drivers for swine, they want farm isolation. I didn't necessarily mention this, but farm isolation means getting pigs away from other pigs, because then that decreases the chance and risk associated with disease transfer from one herd to another. So if you think about where our animals were historically, moving north and moving west for the swine industry makes sense because they're moving away from other pigs. Also, we have these social forces, right? We talked about the potential for odor conflict and how that can influence where pigs go. In our odor planning world, pigs smell worse than chickens. So moving them away from people, which is north and west in this scenario, also can help with odor. With manure shed wise, they are also in the swine industry seeking farms that need manure nutrients. So they want to move the swine to a source they want to move the swine source and establish it at a sink area. And they want farmers that are going to be better stewards of that liquid manure. And why would that be? Because it's liquid, right? Many of us in these industries know that hauling liquid nutrients is a lot more expensive than hauling solid. Poultry industry, they have the health, animal welfare, and consumer product things that influence animal transport times that we mentioned. That's why they want to stay closer to home. But poultry litter is routinely transported because it's solid manure from source to sink areas, and some to the mushroom industry, because we see that litter has a demand and can be sold. So kind of a recap here. The swine industry is impacting manure shed distribution by moving animals. The poultry industry can influence distribution of their manure shed by moving the manure. Our stakeholders, right, including producers, integrators, universities, agencies, can influence future manure shed locations and impacts, and we need to think about that. In the animal world, in the biosolid world, maybe you can use some of these concepts to think about what you're saying, what you're doing. One of the things we said in our paper was that, if we're going to have pigs moving north and west, and we want to continue to influence them moving out of this concentrated area and moving the manure nutrients towards sink areas, if we want to do that, what could we do? Well, one thing we suggested would maybe we need slaughter capacity to move up here. Another thing would be maybe we need a feed mill in that area. And indeed, if you are familiar with the intersection of Route 80, Interstate 80 and 15, you'll see a construction project going on right at that spot. And it is nearly a $50 million feed mill expansion, which will take nutrients from corn and things from other parts of the country, bring those to central PA, and then distribute them into these sink areas. So actually, it's influencing the manure shed. We see that coming through. We also thought in this paper and talked about swine industry technologies. We know that liquid manures contain a concentration of phosphorus that is higher in their solid portions. So whenever we separate out the solid and liquid portions of the manures, the solid portions have more phosphorus. There are technologies, and many of them come from the biosolids industries, right, that can extract phosphorus but the capital and operational costs of these are not quite economic to influence widespread use. We just don't have the economics figured out to make it profitable at the farm. So it's not done as much as we'd like to see. Some dairies do separate solids and are able to use them for bedding, but when they use them for bedding, that does not leave the source area. Those nutrients recycle within the same farm before moving to the field. In the South, we know that swine lagoons do allow solids to settle, sometimes for 20 years before they have to clean those solids out, which are phosphorus rich, and move them on. The poultry industry, they do enhance drying during production. So we have fans and ventilation and systems that are enhancing drying so we can transport the litter. And then we do have a few pelletizing plants that exist. So I'd like to give you some food for thought as I come down toward the end of my topic, right? These are not the solutions. These are not necessarily definitive things. These are questions or thoughts that maybe will allow you to see the big picture and relate my story on manure to biosolids, right? Biosolids and manure have this often similar destination, right? We want to put them on the landscape and on an agricultural field. And if we want to do that, we will have to, as we started out talking about, think about the phosphorus cycle and put those constituents into a manure or nutrient management plan. And in many cases, as we do that, we'll see, if you run the balance on what the crop needs and what the organic product is supplying, we know that we are hoping to replace fertilizers. The fertilizer industry is probably not liking to hear that, but that's the world we're in. And just some questions. How do you discourage fertilizer use and incentivize manure and biosolid use? What are the things that we can do, programs that can be implemented? Can fertilizer companies partner with dry manure and biosolid distribution, right? Some fertilizer companies that sell and apply fertilizer and lime on a contract with a farm may also be able to apply dry manures and biosolids. And I see that there might be opportunity to work with people to move some material to storage areas in sink areas where the nutrients are needed. And if we can set up infrastructure to allow those to be applied, we might help them out, and in turn can replace some fertilizer nutrients that can benefit the farmer economically, agronomically, and help our world environmentally. Incentives, right? Can we provide incentives? I see a lot of dollars right now in the agricultural world going toward best management practices that are geared toward an acre of land, toward some specific item on the farm, but I see very little of it providing incentives for people to move manure nutrients from a source area to a sink area. And in the long run, it really doesn't discourage or change our big picture problem. Our big picture problem is that we have more phosphorus in our source areas than the sink areas, and can we move that, right? So maybe first-time users of biosolids receive some kind of incentive, and maybe there's some kind of incentive to move manure or biosolids from a source area to a manure sink area. And finally, here, a big long thing up is manure subject to the P index, right? If we're talking about phosphorus, we need to think about the phosphorus index. And this is something that is used on many farms. The farming community understands the phosphorus index. They are subject to use it, forced to use it, if you want to call it that. Could it increase planning and smart use of biosolids? It comes with a cost, right? But that can be viewed as a disincentive. But if you're a regulator or have an environmental slant thing from an environmental standpoint, you could view it as an incentive to move nutrients to sink areas, because those people that need to develop a plan might be less likely to do it if they are in a source area because they have manure available as a cheaper alternative. So with that, I guess we're going to save questions at the end. Here's my contact information, and I thank everybody. I'll turn it back over to Bill. Thank you.
Thank you, Rob. That does challenge us to develop liaisons with the agricultural community. And so thank you for that particular frame of reference. So let us go to our next speaker. That's going to be Gerhard Fossner from CNP Centrisis. I think CNP stands for carbon, nitrogen, and phosphorus, which is not surprising because Gerhard has been the go-to person for me on understanding the evolution of phosphorus recovery technology. And he leads CNP in that endeavor to recover and combine that with thermal hydrolysis in wastewater plants. Gerhard's a native of Austria, former graduate of Kapfenberg Technical College in Austria, electrical engineering degree, and then he has an MBA from Queen's University in Charlotte, North Carolina. And Fossner began working with wastewater and water and sludge treatment in 2001. And he believes that there is no waste in wastewater. And so he's committed to recovering these nutrients and energy in our systems. So Gerhard, give us a little background of what we need to know about the technologies to remove nutrients from our wastewater.
Yeah, thank you very much. Can you all hear me?
Yes, can hear you very well, very clear.
Okay, my screen, you can see my screen?
Not yet.
Not yet. Okay, sorry about that. So you hear me, but you don't see my screen. Shit.
Well, I see your face.
Yeah, well, that's not as important as my screen, so.
I think it's coming up.
Okay, good.
It's not in presentation mode yet. There we go.
There you go. Okay, great. So thank you very much. Thanks for having me. Thank you for everyone joining. So I think it was a nice introduction from Rob. I love this gaining the agricultural point of view and the sources, and some of that you will find in my presentation. But I thought what I would do is I try to give a little overview on how the landscape looks on our water reclamation facility. Some people call them wastewater treatment plants. I don't like the word. I call them water reclamation facilities because there is really no waste there. So, but what do we have? You know, we talk about recovery of phosphorus bill. We want to recycle it, want to be less independent. So what opportunities we have at our own sources here domestically to get this product out. So I give a little overview here today. My goal is to show you, you know, what does it look like, the phosphorus at the US water reclamation facilities, how much do we have? I have to talk a little bit about the technology on how to recover phosphorus compounds. What kind of forms of phosphorus do we have at water reclamation facilities? What are the fertilizer properties of phosphorus recovered from those facilities? Trying to make an economic case, because like Rob pointed out before me, what is the economic case to recover those products? And then finally, what are the challenges and opportunities for phosphorus recovery? So those of you who are active in our industry, you notice very well how phosphorus recovery works. But for those of you who may not be so familiar, when we talk about phosphorus recovery, we have two options at our water reclamation facilities. One is a chemical phosphorus removal where we use iron or alum salts to bind the phosphorus. That phosphorus then would come out together with your biosolids or cake. Or we have an options to do a biological phosphorus removal where we intentionally enrich the waste activated sludge with phosphorus to take up as much phosphorus as we can, staying in this cake. And then we have an opportunity to recover that phosphorus in different forms, which I'm going to talk later about, and beneficially separate the phosphorus from the cake solids. So this is wonderful. So the advantage is when we have a bio-BN anaerobic digestion, for example, we can have a lower reliance on chemicals, and we have phosphorus recovery. The unintended consequences, if we would not recover the product or we do know nothing about it on bio-B, is that we have struvite formings. Struvite is a combination of magnesium ammonium phosphate. So this phosphorus gets released in an anaerobic environment, and then it forms struvite, and the struvite scales pipes, scales dewatering equipment. So it's a lot of struvite related nuisance. Also, that goes back to Rob's thing about farms. A lot of dairy farms really struggle with that when they do like anaerobic digestion with this manure, because it really precipitates the pipes and clogs them, ruins all the dewatering equipment. And then also the other unintended consequences, if you don't remove it before dewatering, is that elevated phosphorus concentration stabilizes your extracellular polymeric substances. So those are your proteins, your sugars, polysaccharides. And the higher the phosphorus concentration is in a biosolid, the worse the waterability it is, because higher phosphorus concentration means more water binding ability by the sludge, less letting go of the water. So the higher the peak concentration, the worse is your dewatering performance and the more polymer we will use. So there's an economic incentive for plants, certainly also remove phosphorus, and it's probably the main driver to remove the phosphorus from their plant. So, but when we look at where's the phosphorus going in a wastewater treatment plant? So when we say 100% comes in, you end up 10% of that phosphorus, it can be found in primary sludge, 10% is in your effluent, in the outlet, and 80% of this total phosphorus is gonna accumulate in the waste activated sludge, which then obviously on anaerobic condition or some other change in pH, acidic condition will be released. So if you want to recover phosphorus, we focus on the waste activated sludge to recover that phosphorus in a water reclamation facility. So when we did a WRF project where we showed phosphorus recovery with acid phase and dicalcium phosphate at Madison, Wisconsin in 2018 or so, 19, we asked the participating utilities, what is their goal? What would they like to see by removal of phosphorus? And those participating utilities were mostly larger plants. So there was the Island, Boston. So there was Denver Metro, the Hyde plant. There was Nine Springs, Madison, where the pilot was conducted. And there's the other plant was Milwaukee Metropolitan. So we asked them, so what are you trying to get out of it? The first thing they were said, of course, we want a reduction of the phosphorus load in the cycle. We don't recycle the phosphorus back from the centrate. We want this out. We want to control struvite by removing the phosphorus source before we go in an ideal anaerobic environment. We want to improve our dewatering efficiency of the biosolids. And here it is, Rob, what you mentioned already. We want an improvement of the nitrogen to phosphorus ratio in biosolids, because especially in Wisconsin and other places, most people, Rob pointed out nicely, have way too much phosphorus in the biosolids, not enough nitrogen. So what happens if you could shift more to nitrogen, less to phosphorus? That would allow them to apply more phosphorus on the existing land. So that would be a huge economic incentive for those plants. And then, of course, people said they want phosphorus recovery to produce a valuable fertilizer. So what are the phosphorus forms, what we mostly see in water reclamation facilities? So there are two main ones. The first one is brushite. So brushite is dicalcium phosphate. So it forms on a slightly acidic conditions of 4.5 to 6.5. Is a very good slow release fertilizer. We go to the properties a little bit later. And the other one, the most common removed one at this stage, is struvite. So struvite is magnesium ammonium phosphate hexahydrate. So you have ammonia, phosphate, magnesium. It forms obviously usually, in an anaerobic digest and past anaerobic digestion. It forms on a slightly alkaline condition, really 7.5 to 8. And it's a very good slow release fertilizer. There's also hydroxyapatite, which is at the higher pH concentration, but for the purpose of this discussions, we want to focus on brushite and struvite. So, how would this look in reality when you try to remove, for example, post anaerobic digestion struvite? And this is our technology, so it's called MACBRAX. So what you hear is a little diagram. You have the biological treatment process. You have an anaerobic digester. This technology is a phosphorus recovery post anaerobic digestion. So we take the digest state, we feed it into this MABA reactor. In the reactor, we create the ideal struvite forming conditions with the right pH. We strip the air out, we elevate the pH with dose magnesium, which is always a limiting agent. So we look how much more phosphorus we have, and then we made it up with magnesium. And then the idea is to form struvite crystals. And then you have two options. The first option is you recover the struvite. You see this little triangle here, phosphorus recovery. And I do this like, let's see if I can do this like, okay, there you go. Oh yeah, Rob did this. So we have phosphorus recovery here. So it can come out in form of struvite. And then the second option you have is you can sequester it. That means this detention time of this vessel is smaller because that dictates the crystal size. You leave these crystals in suspension with the digest state, and then you bring it to the dewatering step, and then the phosphorus comes out with your dewatered biosolids. That's the most economical way of dealing with it. But as Rob pointed out, if your phosphorus index, that may not be a good solution if you drive the phosphorus now in your cake solids, and then you limit on land application of that phosphorus. So here, get it out of it or sequester it. Also, then another advantage of this is we intercept the side stream reduction, so we don't recycle the majority. There's about 25 to 30% of the total B load goes back to the front of your plant. Once you intercept it from the struvite, it's out of the liquid stream, so you get a nice stable bio-B operation, and you have an opportunity to also then meet your low phosphorus concentration on the back end. Oh, so my screen, why is this not moving? Sorry. Oh. Can you all hear me still?
Yes, we can hear you. We just
Okay.
can't
The
see you advance your
screen is-
slides.
I'm sorry, the screen is stuck. Let me see here. I apologize for that.
Maybe what I've done is I just click on a screen and use my arrows on my keyboard to advance the slides when I'm using that drawing tool.
I used to, yeah, I'm trying to do this, Rob. Like, let me see, boss share, new share. Let me, maybe I. Was not planning on that. Sorry about that. Oh, there you go. Okay, sorry about that. So I do escape button for whatever reason. So when we look at about struvite recovery, is it worth it? So that's a question, right? When we see this is a feedback or was analysis done by, I think Leon Downing did this as part of this WRF project. They looked, okay, what are the payback implications of struvite recovery? And you see here the vast majority comes from biosolids dewatering. So, you know, getting drier cake solids, prevent struvite precipitation, reduce polymer concentration. Really only 10% of this whole RI, if you will, struvite accounts only for 10%. So for a lot of people, they say, well, you know, if it's only 10%, is it worth to recover, or should I maybe sequester? So that's the question what we have. And to move on, and then what I want to say with that, so if you leave the anaerobic digest as solubilization for phosphorus, maybe it's not the most efficient way. But what happens if we have a fermenter upstream of the digester where we drive a low pH and get a very high solubilization of phosphorus? And what you see here is those are tests we did in 2018. And what you find is that you have about, you can achieve up to like 85–90% of solubilization of phosphorus. By that we mean total phosphorus coming in, 85% of that phosphorus becomes ortho-B. So could be recovered, obviously with inefficiency, with recovery, but you may end up of this 100% recovering 55% is B, versus you probably can only do 25% with struvite, so post-digestion. So this is a big one. So one of the technologies you may have seen is Ostara, is the Wastewater process. So Ostara uses a B-release tank, anaerobic release tank. The goal here is to solubilize the phosphorus at a low pH environment. So they achieve about 70% on average solubilization. So you take a very soluble phosphorus-rich liquor, you thicken it and you run it through the Ostara reactor, and then you bring in the ammonia from the anaerobic digest to form a struvite burdle. And then this product gets dried and bagged and then is sold as struvite fertilizer. So that's one technology when we talk about struvite. The other one is our technology, the other one is called Calprex. So here we recover phosphorus in the form of dicalcium phosphate. Similar situation, you have a B-release fermentation tank, low pH, you drive the liquor in a centrifuge, you separate the solids from the centrate, phosphorus-rich centrate goes into a Calprex system in a tank where we dose calcium hydroxide, bring the pH up, bring the calcium source. The two elements react and form dicalcium phosphate, and then we can separate it again, and then you have your recovered brushite. The interesting thing here is that brushite has 18% phosphorus, B2O5, versus struvite has 12, so you have 50% more phosphorus in this product. It has no ammonia in it, so you can dry this product whatever you want. You can pelletize it. It's a very good slow release fertilizer as well, and the advantage is, and you see later, you have much better recovery efficiency of phosphorus ahead of the anaerobic digester as compared to struvite. So for Denver, making the case here now to give an idea how much phosphorus the treatment plant. So Denver Metro is about serves 2 million people every day. They get about 7,000 pounds of phosphorus into the plant every day, and 1 pound of phosphorus equates to 8 pounds of struvite. So potentially, this plant forms 56,000 pounds of struvite every day. So this picture shows you a pipe with struvite scaling. So they decided they want to do something about the struvite. Here's a little diagram. I don't want to bore you with all the data, but look at the blue diagram. So without any recovery, they would have 1,300 pounds of phosphorus could precipitate in their digester. So this is just B, right? So that means almost 10,000 pounds of struvite. So that's something they did not want to have happen. And then also the side stream load contain up to 26% of the total B going back to the front of the plant. So they want to really intercept the side stream. They want to protect the digester some and get some of this phosphorus out. So they don't have to recycle the phosphorus. So two options we looked at. And the first one is this Magprex. Remember the post-anaerobic digestion process, which really the main concern here was reduction in phosphorus recycle. So take it out of the side stream so it doesn't go back off the front of the plane. But we recover about 404 pounds of B as struvite. So give and take 3,000 pounds of struvite, okay? I recovered there at this plant. And however, if we would have gone to Calprex on the right-hand side, you see that we would be able to recover like 5 times as much of phosphorus in the form of brushite. So this is, if your goal would be recovery, the fermentation step ahead of the anaerobic digester would be far superior. But that at this time, when we put the system in about 3 years ago, that was not the main objective, was the waterability and was the side stream control. But for recovery, the right-hand diagram would be the way to go. Both pre and post digestion can reduce side stream loads and reduce struvite formation potential. That applies always. So going back to what I mentioned earlier here, the NP ratio of in the biosoils affect the application rates, which is based on the quantity of phosphorus. So we modeled the total P removal at Denver, Madison, Milwaukee, and Boston at this WRF 5004 projects. And what we found is, and that's the really interesting one, a change in the NP ratio results in the ability to increase the fertilizer application rate by 29 to 73%, depending on the configuration of the system. So that means if our goal is to really apply more solids on land, a pre-digestion of P remover would be a great ability to have, to take more of the P out, increase N, and that allows you to apply more solids on existing lands or have less land to apply what you have already solids wise. So you can customize, depending on the removal rate, how much phosphorus you would have in this final biosolids product.
Gerhard, I was wondering, this is sort of like the end of the 20-minute period. I was wondering if you're wrapping up.
Oh, okay. Yeah. Is it already 20 minutes? Okay.
Yeah, it has been.
Thank you. Okay. Okay, good. So we looked at the, at the value of this fertilizer, and what you see here is the brush size is very similar to magnesium ammonium phosphate in terms of its viability. It can be substituted. It's safe. So we recovered it, and we found it meets all the 503 regulations, class AEQ. Here is really one thing that's probably my last important one I want to show you. So let's say if we go and remove this phosphorus, what are the opportunities? We get 1.1 million tons of P into the facility. If we say we can recover 55%, which is doable, and $500 a ton, we could yield $300 million per year of revenue from our municipal sources. But if the market is attractive, the fertilizer safe, why don't we recover more? And I think it's the same discussion we have had. PFAS, Class A designation, is it Class A or not? Offtake agreements, plants are really not in the fertilizer space. Additional equipment and operational expense for these folks, and then really I think unfavorable regulation for local land applications. So the idea would be to use the phosphorus where we produce it. I know that's not easy, but that would be the ideal kinetic situation to reduce the ways to transport the material. And this is it, Bill. Just want to thank to these folks here who contributed to that, and that's all I had. Thank you.
Well, thank you, Gerhard. That really does help cover the bases on how we can make a better biosolids through phosphorus extraction. So on to our next speaker. Bryce Meeker is the president of Northeast Biochar Solutions, and it was with his presentation on how the char or ash from thermal processes is different from that of other kinds of biosolids that had me ask him to make a presentation today. He is a lifelong business developer in the pursuit of world habitability, and he is a dedicated environmental entrepreneur with over 18 years of experience in renewable energy, both in the United States and in Ukraine. He has a MA from International Business from the Fletcher School at Tufts, and a BA in Economics and International Studies from the University of Kansas. So welcome, Bryce, on your presentation on P-bearing fertilizers from thermal processes.
Thank you, Bill. Everyone can see my screen?
Yes, we can see your screen. Thank you.
Well, let's start a little blurb about us, kind of an overview. Carbon fertilizer manufacturing turns this biosolids disposal problem into sustainable soil restoration solution. It does remediate biosolids for an endpoint for PFAS and contaminants. I know I'm not supposed to advertise that here, but produces a beneficial biofertilizer. This sequesters carbon and restores soil. Achieves a negative greenhouse gas footprint, so it's climate friendly. And it meets the strictest air quality standards nationally, mainly in New York State CLCPA. Climate Leadership and Community Protection Act. I just had to include this on peak phosphorus. It's a concept that describes the point in time when humanity reaches the maximum global production rate of phosphorus. This is kind of how the industry views this. Based on estimates of available rock phosphorus from Morocco, basically. And it describes phosphorus as a finite resource that might negatively affect the world's food security. Basically, it's a marketing scare tactic the industry has been using to basically bolster the price of phosphorus. But the concept does not recognize renewable forms of phosphorus, nor the excessive amount of wasted phosphorus in waterways. And mammals, including humans, as we produce phosphorus, agriculture operated for over 10,000 years without mined phosphorus. And phosphorus fertilizer bans are now being used to reduce phosphorus runoff. And one example is that the New York State nuclear runoff law prohibits the use of phosphorus fertilizers on lawns. Retail consumers are constrained for using phosphorus fertilizers except for establishing new lawns, and therefore the fertilizers require special labeling requirements. Professionals, farmers, and commercial operators are not constrained. The law is based on chemical/mined fast release fertilizer properties. So we're kind of being lumped into that. Exempting our fertilizer is beneficial but not necessary, just because it is up to the consumer to comply. But what we're trying to do is address soil degradation with our fertilizer, and escalating use of chemical fertilizer, particularly phosphate rock, is degrading soil globally. It's commonly bound by salt, which is corrosive and dissolves in water. Escalating use over the last 80 years has resulted in soil degradation virtually everywhere in the world. And replacing chemical fertilizer with carbon, and this goes for manure-based fertilizers as well, reduces the salt loading, increases soil organic matter, carbon, soil biology, and reduces runoff and erosion. Basically, we've got to reevaluate the use of chemicals, I think, in agriculture. And there's value in transformation with the way we see it. Biosolids are nuisance, non-hazardous waste today. It's an age-old problem that's constrained by contaminants, regulatory air requirements, and climate change. It's a growing disposal cost for municipalities. But biosolids biochar is a highly desired and valuable biofertilizer, soil restoration, and soil remediation solution. It's got a lot of uses. It replicates the role of manure fertilizers in modern agriculture and horticulture applications. It reduces chemical fertilizers degrading soils. And it rejuvenates soil biology, microbes, and fungi, and improves soil resiliency to climate change. So we've kind of designed our fertilizer a bit more around what is actually in demand in the agricultural sector. They produce solutions that they desire solutions that reduce soil, rebuild the soil, reduce costs, and improve yield. Reduce nutrient application, improve hydration, and reduce erosion, increase soil resiliency to climate change, and utilize existing assets and equipment. I mean, the last is very important. They don't want to go buy new equipment just to apply my new product. And NBS has tailored its product to meet the needs of these producers. On-demand nutrient release. And that's kind of something we may want to copyright. It's beyond slow release. It really is on-demand release, and I'll get into that in a few minutes. But it restores the soil organic matter and carbon, which has really been lost in the chemical age we've been in. And improves the soil moisture retention, which is a key thing to being more resilient. You need, and I mean, we're, in western Kansas, for instance, where I'm from, the aquifers are drying up. It's about over. Reduces nutrient runoff losses and erosion, and is compatible with existing assets and equipment they already have. That's, again, very important. So our process, the biosolids received from wastewater treatment plants and chipped wood waste from municipalities. We have a couple resources. We mix them together. The wet feedstocks the feedstock is sized, mixed, and dried together prior to drying. The dried feedstock is then sized and heated in the absence of oxygen or pyrolysis kiln to avoid combusting the solids. That's the key thing. We try to recover as much solids as possible. But we're removing PFAS and all other VOCs, because PFAS is the most difficult to remove of VOCs, by reaching about 1100 to 1250 Fahrenheit material temperatures. So in that pyrolysis phase, we're getting it hot where all these contaminants sort of evaporate into a gas. And that generates pyrogas, which is remediated at 2300 degrees to destroy the PFAS and other VOCs in it. So this is something we're pretty unique in the industry is we're actually able to remediate it from the material, air, and water emissions. Maximize the solids recovery to minimize air and greenhouse gas emissions while ensuring full PFAS or VOC separation. So we kind of find our sweet spot operating we want to basically clean the material and we don't want to burn any more solids than we have to. And the carbon fertilizers in cooled, hydrated, sized, and packaged to produce marketable products in multiple niche markets. So what is carbon fertilizer? It's sort of a multi-use biofertilizer product. It's a standalone biofertilizer for lawns, garden, and agriculture. It's easy to apply in a granular form, low dust, compatible with common fertilizer spreaders. The key difference is it binds nutrients with organic matter and carbon versus salt. And in that sense, it feeds the microbes and fungi from the organic matter, and it restores the soil biology. And it permanently improves water and nutrient retention with the fixed carbon in it that basically is around for about 1,000 years. It also provides a nice soil remediation solution. So it's got this sort of high cation exchange capacity that tracks other compounds to it, including nutrients. It helps with nutrient uptake and delivery in roots. But it also helps to transport contaminants into those roots. So if you're in a soil remediation solution, the same nutrient properties benefit, more or less attracting and immobilizing the contaminants for phytoremediation to occur. And so it improves that aspect. Also, it's also a horticulture solution. It replaces peat to grow medium. Peat has a very negative, very positive, very large environmental footprint. But it really helps with very high emergence in healthy plants. It's also a seed coating. And accelerates early stage root and plant development. I mean, that's what biochar is really known for, quite frankly, is the effect it has on plant roots and just causes them to explode. It delivers oxygen, among other things. So what is biochar? It's produced by pyrolysis or gasification typically, or incomplete combustion from, wood boiler systems, etc. Composition and size are functions of feedstock, thermal treatment, and material handling. The fixed carbon content is the portion that degrades over centuries and is used to evaluate greenhouse gas sequestration potential in soil. So it's the part that sort of sticks around and has a permanent effect on the soil, which is beneficial. Wood biochar is the most common biochar produced. It's got a very high fixed carbon, ranging from 65 to 90%, depending on the species of wood and bark content. It's low ash, nutrient, very low CEC value, cation exchange value. It's basically just carbon. And as such, it requires inoculation with organic matter nutrients prior to soil application. Biosolids biochar, on the other hand, is really high ash, high nutrient, high cation exchange capacity material, but it's got low fixed carbon. But the nice result is it does not require inoculation prior to the soil application. You can just apply it as is. You don't need to add anything to it to do anything. It doesn't require anything fancy. The high cation exchange capacity we've been talking about, the biosolids contain these different nutrients and minerals which have positive cation and negative anionic charges, like nitrogen forms, potassium forms, phosphorus forms on the anion side. These basically benefit the exchange of nutrients and contaminants with plant roots and the retention in soil. It helps the plants literally attach onto nutrients and transfer nutrients from the soil to the plant roots. Same with contaminants. Carbon fertilizer produced predominantly from biosolids, but wood also adds value. It increases the fixed carbon content, greenhouse gas sequestration, offsets natural gas use, lowers OPEX and greenhouse gas emissions, and helps manage heavy metal content as well, which is useful in the biosolids industry. And we've kind of made carbon sequestration easy with it, a drop-in substitute. It's compatible with regular spreaders, it's easy to fertilize and replenish and sequester in one step. And you're really doing a replenishment versus degradation, which is the way we look at it. And it's simple application, just like any other fertilizer product, no inoculations required. But it's more than a common fertilizer because it manages nutrients and contaminants. Like the high cation exchange capacity attracts and interacts with nutrient contaminants in the soil. The porous structure helps to mobilize the contaminants and reduces runoff. So they kind of the properties work together. And the roots are really attracted to the oxygen, water, and nutrient contaminants in the carbon. So, basically, if you think about this, particle gets wet, the roots seek out the moisture and find oxygen, nutrients, and contaminants if you're in a phytoremediation mode. And so it feeds the plants and restores the soil at the same time. The organic matter feeds the microbe and fungi to improve moisture, nutrient retention. Nutrients are released on demand as the plant roots literally tap the material. Again, there's no leaching with this material. And roots extract contacts and extract contaminants and vegetation, removes them from the soil eventually. By the way, the pyrolysis process provides an endpoint for the biomass as well if needed. It's got a lot of contaminants in it. Biochar benefits really early stage root and plant development. It's great to start plants, but it really causes the roots to explode because the carbon is delivering the oxygen, water, and nutrients, which really excites it and it creates healthier plants. And there's tons of research on this, but you can see the difference in the plant root volume and just how the plant roots like to grab onto the carbon, how they tap it. So just compared to dried biosolids, which are already commercial, despite the contaminants and odors, our process remains the PFEs, and it actually eliminates the VOCs that cause the odor. So we never have any odor or any contaminants in it. One thing I wanted to mention is the soil carbon amendment program. We talked about how do you get farmers to use these kind of things. Well, the USDA has a nice little program that provides a $220 gross cost per cubic yard, of which 75% is reimbursed by the government. And so, if you're at 220 bucks a ton, that ends up creating a nice demand for carbon. Now, I just got to say on a side note, we responded to a request for information from the NRCS last year and got biosolids into it. It's the first time the government's, I think, ever listened to me. So I like to tell that quick story. But New York is a participating state. Biosolids are specifically denoted as acceptable feedstock. Other manures would be as well. And the SBS facility qualifies to market its initial production through the program. We're expecting a 377 bucks per ton, given our costs or given our density. And last but not least, what we're doing benefits climate change. We generate 3 credits to reduce greenhouse gas emissions 237% relative to the gross emissions of the facility. So our net reduction is 137%, which is really large for just about any industry. It's carbon negative. So we avoid the disposal emissions that would otherwise be incurred. We displace greenhouse gas emissions from fertilizer production, chemical fertilizer production, and we sequester carbon in soil where it's actually needed. And that's the biggest credit we receive. So in large point, the carbon fertilizer receives a carbon negative footprint, wind and solar are carbon neutral. I mean, traditional industry is positive, just to put it into scale. So that kind of concludes my presentation overview of it. I know there's probably more questions on the pyrolysis, but just integrating, Garrett, I think, there's some interesting things, problems I think that phosphorus recovery does kind of help us out upstream. One aspect about this technology is it doesn't prefer anaerobic digestate. So taking the phosphorus out and the struvite out would help balance the NPK of our product. And it would also shift that VOC to solids ratio back in favor of something that's more economical for us to process, if you will. So I'll leave you with that. Well, by the way, this process could be used on any animal manure as well, but it will be a little while before we get the cost down to probably service that industry.
Thank you, Bryce. And so if I just make sure I understand, we do not yet have a production facility producing a product like what you are discussing. This is still a promise.
It takes a long time to permit.
Yes. Right.
So we're at the final stages of permitting our project in upstate New York in the Moreau Industrial Park. It's in South Glens Falls, New York. Mm-hmm. We're hoping to be online summer of 2025.
Okay, thank you. But it does tick the box that Rob's challenged us with a product that is dry enough that it can be transported because of its high value
Oh, yeah.
beyond where the phosphorus is built up in soils close to the
Yeah,
animal
and
operations or
and
close to cities.
we're finding there's a lot of demand, kind of like Milorganite for bagged product. You know, there's a lot of gardeners want it, horticulture wants it. You know, it's a usable form for landscapers, etc. There
Okay.
seems to be markets for it.
Well, thank you very much. And we'll go on to our final presentation. If I could, I'll introduce Persephone Ma, now with Brown Caldwell. I got to meet her first as a graduate student working with sewage sludge incinerator ash and demonstrating the phosphorus fertilizer capabilities of it. She's a soil scientist and environmental engineer with Brown Caldwell now. And she completed her PhD at the University of Minnesota in the Soil, Water, and Climate Department. And she was studying the agronomic potential of the ash. And she has taken various routes with biosolids residuals in the past, having worked with McMaster and Carr, the Royal Botanical Garden at Kew, and the Argonne National Laboratory. And so she's excited to talk to us today about the impacts of SSI ash as a soil amendment. So Persephone, take it away.
Thank you so much, Bill. And also thanks to all the other presenters who laid this wicked problem of phosphorus out for us. As Bill mentioned, I'm going to be talking about a whole other direction that we could go to sequester phosphorus from a wastewater treatment plant and from our overall system, which we'll talk more about. So it was mentioned, but I thought I would go into a little bit more depth that phosphorus is incredibly important. The DNA and RNA is built on phosphorus backbones. The actual energy currency that living things have in our bodies to get things done is also based on phosphorus. And it means that it's also incredibly important for farming and for our food systems. So on one side of the screen, you can see a very large soybean. That is actually soybean that was grown with phosphorus, and the other side is soybean that wasn't grown with phosphorus. It can be that dramatic. Phosphorus in a plant system is important for rooting structures, for fruiting, for yield, things that are very important to farmers. This picture, one of the things that's sort of been mentioned that I wanted to touch on was this idea of chemical fertilizer versus other kinds of forms. One of the phosphorus is great. It's very important to us, but it's also very complicated, which is why I kind of love it, especially in the soil system. Let's say traditional off-the-shelf phosphorus fertilizers, it is 100% plant available. Basically, the farmer wants to say, I'm going to take this off the shelf, I'm going to put it down, and the plants can have it. Unfortunately, it's not that simple. When phosphorus hits soil, the vast majority of it will move to forms that are inaccessible to plants. Rob's original sort of soil phosphorus figure that he showed all those different forms that it goes to. Often, most of the time it's mineral, sometimes it's organic, which basically means that we're playing this game when we put chemical phosphorus fertilizer on, that we want it to be there, we want it to be there in the right time, in the right place, in the right form. Because when it's not, and it goes to places that we don't want it to be, we are all familiar with eutrophication, the algal blooms, fish kills that can happen when phosphorus ends up in the wrong place. And this ties all the way back to Rob's idea of we want it in the places that need it, which are the phosphorus sinks, but we don't want it in the places that have too much. And oftentimes this burden really falls to you all in wastewater treatment plants or water reclamation facilities, that you are responsible for being the keepers of the waterways. And you bear this burden in your NIPDES permits every year of moving the phosphorus from the water to the solids, let's say. You either separate it out with the existing processes or the new technologies that we just heard about today from Gerhard and Price. And I will take this opportunity to say that environmental phosphorus, sort of waste of phosphorus in the environment from wastewater treatment plants is actually very small, but it's a point source that's already regulated, which makes it low-hanging fruit and a really easy way for us to start the conversation of circular economy when it comes to phosphorus. So specifically, we sort of walked through this. We mine phosphorus, it's applied to plants, we eat those plants, we animals eat those plants, we eat those animals sometimes, and it goes into wastewater treatment plant. In this form, like I come from a food system perspective, I'm in soil science and agronomy. Wastewater treatments are part of this food system. And so I really studied how does this ash, which I will talk more about, flows this phosphorus through. And so fundamentally, the question at the top is, can sewage sludge incinerator ash be used as an agricultural phosphorus? If you wanted a better look at what this ash looks like, this is sewage sludge incinerator ash from Metropolitan Council in St. Paul, Minnesota. That's where I did my work. They produce 35 tons of SSA a day, which adds up to 3 million pounds of phosphorus a year. However, you can tell from this picture that it is an ash, but it does make movement much easier, especially compared to either a wet or a caked biosolids product. And so it becomes more of a candidate for some of Rob's point of moving through fertilizers from sources. One thing I will also take this time to mention is that there is no carbon in this, sadly, it gets burned off. And there's also no nitrogen, which I think a couple of folks have talked about this nitrogen phosphorus ratio that we're playing with in manure, in biosolids, is a different game here because it's just phosphorus. And that basically allows farmers to have a lot more flexibility in pairing a phosphorus-only fertilizer with another nitrogen-only fertilizer, urea, ammonium nitrate, whatever they like to use. Especially if this is a recycled product, and depending on the economics of the situation, it could be a way to reduce farm costs, which are incredibly high. So in my project, we started at the top. We wanted to determine the plant availability of phosphorus in soil, in SSA, not at SSI, sorry, Bill. We went with SSA. It's referenced as a lot of different things. But we also wanted to look at what are their benefits from, like this is a comprehensive fertilizer source. Does it provide potassium? Does it provide copper or zinc or other things? And so copper and zinc I will touch on, but it also links to, are there environmental risks to applying a human-based wastewater product? There's a lot of regulations on that. What kinds of broader environmental impacts may there be? We looked at the whole, let's say, soil plant system. We did not go into water. We looked at plant biomass with grain and stover. Grain is what you think of with corn. Stover is the green part of it, the non-green part of it, pretty much. We looked at the soil chemistry, what's actually happening in the soil. We also looked at soil microbiology, which I will not talk so much about, but you can ask a question if you're curious. We also did, so basically, I'm not going to go into too much detail about the experimental design, but the thing to know is that we did a 3-year field study in corn and soybean in a rotation that's common in Minnesota. And we had 4 phosphorus sources, which I'll talk about, at a range of rates, 0 all the way up to 2 times what a farmer would probably apply for that particular land in its history, just to make sure we understood exactly what the behavior was at different points.
Persephone, I hate to interrupt your flow a little bit.
That's fine.
The audio is a little bit touchy here. Sometimes I can't catch the end of your sentences. Is the microphone one that you can bring up closer to your mouth, or?
If you don't mind, I'm actually going to plug in a headset and look super uncool. That's okay with you all.
Give it a shot. Do you have a? I can't hear you at all right now.
Hello, maybe?
Oh, now it's beautiful. Oh man, that
Beautiful.
is so much better.
Okay.
That's so much better.
There's always a trade-off. But thanks for letting me know. And if I'm not going to go back, but if there are questions or, Persephone, you said this sentence and then the end, I can fill that in afterwards. So you can still hear me? It beeped at me. Okay.
Yeah, it's very clear now. Thank
Okay,
you.
lovely. So we looked at 4 phosphorus sources total, including the ash. We had the sewage sludge incinerator ash, which we did add some water to make it usable. This is like a baseline. You take the ash from the plant and see what happens. We also use triple superphosphate, which is a phosphorus-only fertilizer. We had Class A pelletized dried biosolids, also from the same sort of region, from the Metropolitan Council water system, and struvite, which Gerhard mentioned, which is also a wastewater treatment product that comes out. So even before we started this study, we just did some back of the envelope calculations of what are we working with. One of the biggest things that we noticed, and I noted here, all soil amendments were applied based on citrate soluble P concentration. Citrate soluble is the industry standard for testing what plant available phosphorus is available in a fertilizer. It's kind of a proxy test, but it's what is actually reported on a fertilizer bag. So you will notice on the left side of the screen that for SSA, the available phosphorus is only about half compared to the total phosphorus that's in the ash. So TSP, like I mentioned, it's 100% plant available. That's a chemically treated off-the-shelf fertilizer. But SSA isn't, just based on its feedstock, its how it's produced. And so what we ended up doing for this particular study is we evened it out for available phosphorus. It did have some impacts, which I can talk about more, but that's something that I wanted to point out and be upfront about. The other thing that we were looking at when we just looked at what we're starting with was that if you look at the concentrations of copper and zinc in SSA, it is incredibly high. Copper and zinc play this really interesting role in soil science where it is a 503 metal that's regulated because at really high concentrations, it can lead to phytotoxicity. But at the same time, at smaller concentrations, it is a plant micronutrient. It is absolutely necessary to grow crops, so much so that there are zinc foliar fertilizers that people buy if they need it. So this is something that we are aware of. But the other way to think about fertilizers in general is not just the concentration, like if I'm holding a pound of this, how much is in there, but actually how much you're putting onto the field, which is called a loading rate. So when all of these different fertilizers have different amounts of phosphorus, which means you're putting different amounts on. It's kind of like if you have a regular hot sauce versus a really, really hot sauce, you're going to put a very small amount of the really hot sauce. And so here, we actually see that the amount of phosphorus that is added changes significantly, changes the copper and zinc loading rate significantly. It evens out with, let's say, biosolids applied based on phosphorus, which is kind of what we're trying to make the point of. But best practices now are biosolids applied based on nitrogen, which is the -P-N asterisk. And so you can see that even with this particular biosolids that we were using, if you apply it based on normal practices, you're applying a lot of copper and a lot of zinc. Similarly, on the left side, what we do end up seeing is we're putting on more phosphorus based on the way that we have designed this particular study compared to TSP. But you can also see very clearly that applying biosolids based on phosphorus, it's a reasonable amount. When you apply it based on nitrogen, which would be the standard way, it's a lot. It's too much, probably. So jumping into the actual results. I think Bryce mentioned that the corn yield or yield is something that is very important. And this is fundamentally after 3 years, we have the 3 years and 4 different sources, which are the 4 different colors at the 5 different rates, which is 0 through 160 pounds of phosphate per acre. What were the corn yields that came out each year? And the fun thing about doing soils research and phosphorus research, I learned, is that the results are the results. This is what came out. So in 2017, the only corn that was grown with TSP responded to any changes in fertilizer. In 2018, there was no response in fertilizer. However, in 2019, all 4 fertilizers responded the same way, which was basically the yield at control when you had no phosphorus applied was significantly lower than anything that had phosphorus applied to it, whether it was TSP, whether it was ash, whether it was biosolids. And so for us, this, well, as I was doing this as a student, that was really scary. But also by the end of it, it it gave us some idea of the fact that SSA, let's say after a couple of years, was behaving the same as other phosphorus fertilizers. This is also a study in which like you don't want to see something significant happening with SSA because that means it's different and you want it to be working correctly as a fertilizer. So especially when we have yield results that are kind of all over the place, and in 2017, nothing except for TSP, we also look at the phosphorus concentrations or the amount of phosphorus that's moved from the soil into the corn grain. This is actually a 3-year average, and that line is the average of all of the P sources. Because fundamentally, even when we didn't see a yield response in 2017, we saw that the phosphorus was still moving from the soil up into the grain based on the amount of phosphorus fertilizer we were applying. And that was all the same through all of the sources, which for us was kind of heartening to say, okay, SSA does provide it. The other crop that we looked at was soybean. We actually only grew soybean in 2 years because it was a rotation. They're only 2 years and they're only 2 colors because all of the sources were the same. In 2018, there was a slight, pretty small yield increase for all of the soybean grown with any of the P sources. In 2019, you could actually see a more significant response and then a little bit of a tapering off, which is very standard in agronomic crop responses because at a certain point they don't need anymore. And so, especially since that middle line is what a farmer would probably apply, that tracks with what we would expect as any kind of phosphorus fertilizer was applied. So besides looking at the overall yield and looking at like what's actually happening into the plants, we also looked at what was happening in the soil. So available soil phosphorus is basically a test that you do on your soil that Rob kind of mentioned that says, okay, what do you have here now? What kind of condition is it in? This is also a 3-year average based on the application rates that we put on through those 3 years. And you can see that the application of phosphorus fertilizers, regardless of source, applied phosphorus to the soil in an available form for plants. You can see, however, that SSA did not perform as well as the others. It's something that we are still trying to figure out. It's also not entirely surprising. SSA is it really depends on the type of feedstock and the way that it's made and the characteristics, which unfortunately were not in my purview. So I can talk broadly about what SSA, like what the species actually looks like, but I don't know the species of my particular ash. But that often has a lot to do with how it's released, because how the ash is, I'm falling down a rabbit hole. But basically, the way that the minerals that Gerhard were talking about are structured are basically how strongly they're holding the phosphorus, and that can have a huge impact on it as a fertilizer. So besides phosphorus, we were also looking at micronutrients. I mentioned zinc. So over the 3 years, we saw that applying green, which is the ash, and blue, which is the biosolids, increased soil extractable zinc. It also increased it in the corn grain and corn stover compared to biosolids and struvite. At these levels, this is very much in the plant micronutrient territory. This is not at all in the, oh my gosh, we're going to kill things territory. So we already knew that biosolids provided micronutrients. This is also proof that SSA provides micronutrients. I will mention that I'm not going to show it, but copper acted very similarly to this, which makes sense based on the back of the envelope calculation that we knew that it was there, and then we knew it was going to be in relatively high concentrations. We also saw responses in available potassium as well as sodium for both SSA and biosolids. One of the nice things I think when I was going through this data is the patterns are very similar. SSA and biosolids kind of cluster together. TSP and struvite are very pure forms of what they are trying to provide, but they don't have any other micronutrients. So always the question is, okay, what's wrong with this? We did not, of the 503 metals that we analyzed, we only saw a response in mercury in the soil, not in the plants. Comparing to pre-season when everything was kind of about the same, you could see that SSA was increasing the amount of mercury in the soil on a 5 parts per billion level. So this is one of the things, like, we know that there is mercury. Also, the way that the plant was processed, it dumps their mercury into the ash because it's landfilled at this point. But it also is sort of analogous to the other P word that has already been said, but I won't say, that when you are measuring at really, really low quantities, you will find a response. It depends on whether or not that response has a biological implication. And at this particular level, even with several, like, decades of application, depending on other land management practices, this would not be a concern. This would not be a concern, I guess, for plant uptake. It could be a concern for a citizen. I won't make that call. So I'm trying to think. This was like a high level view of the takeaways from this study. Ultimately, SSA increases available and total P in soil and appears to provide a slow release form of P for plant uptake. It also provides copper and zinc and potentially other nutrients at the level for plant nutrition. It does increase other elements of concern, but not at levels that would be either biologically or environmentally significant. If you were curious about the microbes, it didn't do anything, which is a good thing because we don't want it to mess with the microbes. To connect it sort of broadly, this project was particularly interesting to me because it really talks about this shift in farming practices from slow release and towards slow release and multi-year release phosphorus sources compared to chemical fertilizers. It also shows very tangibly an opportunity to replace chemical phosphorus fertilizers with recycled forms. But it also means that we're going to have more conversations about how we're going to do this, whether we're going to adjust land application best practices, especially when it comes to that nitrogen to phosphorus ratio. And with that, hopefully some of it was intelligible. But yeah, thanks very much for listening, and I'll open it up. I'll give it back to Bill.
Thank you, Persephone. I really appreciate your helping with the bigger conclusions, because that is precisely what I was hoping that you'd be able to close with. And we have sort of run out of time. There is a couple questions from one of our attendees. If Persephone and if Bryce would like to go into the chat, they could probably write some answers back to this participant. But what I'll do is I will close this webinar now with a couple brief announcements, because MABA is continuing to provide good content material to listeners on the webinar series. We have actually our next engagement is with the Pennsylvania News Media Association. We're going again to provide some relevant information to our reporters in the field who are concerned about biosolids, particularly if there is an issue around PFAS in land applied biosolids. And that is on Tuesday, October 24th. It's open to the general public, but we're hoping that you'll encourage your favorite reporter to be in attendance. But our next webinar is Tuesday, November 7th, and it's not at the traditional noontime hour. It's at 1:30, but you'll definitely want to be there, because we have our W4170 group, who are the scientists who have been supporting us for so many decades, a select number of our very favorite people on board to talk about the issues with biosolids and soil health. So look out for upcoming emails and be attendant to our website, because there's so many interesting things there. And again, thanks to Gerhard, Bryce, and Rob, and Persephone for their participation in today's webinar. And so with that, I will close our session at 1:31. That's pretty darn good scheduling here.